Good morning, everyone. How are all of you today? Tired? What? Well, you must be excited then, because today we get to start our new unit. I hope everyone had a good weekend. I'll get your exams graded when I get them graded, so don't ask me. I'm working on it. We're going to start a new unit, Unit 2, where we start diving into more of the bread and butter kind of stuff for statistics, the kind of tools that people do all the time as we reference to. And that will be a foundation when we carry on to a third unit, which is the regression analysis, and that's going to be the heart and soul of your paper that you will write later. So this is sort of a foundational part here. In order to understand this foundational part, we turn to our common distribution we talk a lot about in statistics, and that is the normal distribution. Does anyone know what a normal distribution looks like? Yeah, I love it when people do this. Bell curve, excellent. And this is when I get to show off my awesome bell curve drawing talents, because let me tell you, when you teach statistics, you draw a lot of these. It reflects the kind of common distribution we see of data, where there's a lot of observations toward the center, toward the average, and then they sort of fall off and become outliers off the edges, these tails. We call these edges these tails. It's kind of a controversial thing that we rely so much on the bell curve. You're going to see it a lot later. It's kind of a controversial thing because some people argue that the tails are actually flatter than the equation depicts them. Fatter than the equation depicts them, and that's a fair criticism. But I'm going to teach you the standard way, because A, the standard way is built to excel, B, the standard way is how everyone does it, and C, you can't really criticize the way that we do it until you understand the way that we do it. So, this is introductory stats. Let's stick with the basics. But this idea, this focus on the bell curve, is not a foolish idea on the heart of it. So I opened the notes by showing you lots of different distributions. So let me actually zoom in a little bit more. We can appreciate each of these in time. Here's a distribution of IQ scores. You can see a normal distribution superimposed on it. And here's the actual data in the green bars. And it follows it pretty well, right? A lot of observations here in the center, and then it spills off onto the sides. It sort of, kind of starts out a little bit, deviates, and then it drops off a lot and spreads out. Over here is, I guess they're ultra runners. I don't really know what an ultra runner is, but I found this data. And the height, I believe, is measured in feet. Yeah, height in feet. And you see, again, it's not as clean as the IQ one, but it's pretty good with a lot of observations in the center, and then it drops off. This one is from the Department of Transportation. I guess they took a bunch of people, had them drive, and then showed a red light, and then measured how quickly it takes for them to react and start pressing on the brake. And so that TTSL is time to stop. I don't know what L stands for, but it's a measure of that measured in seconds. And again, we see that it's a little noisy, but it still follows that basic pattern. And is 191, so we have 191 observations. We got price distribution by bedrooms. So these are 2-bedroom houses, 3-bedroom houses, 4 and 5-bedroom houses, and then 2 and the 3 where there's the most observation. You see a pretty clear normal distribution. This one's a little skewed, right? This one is a little noisier, but you see that basic story. This one, not much is going on at all. It's hard to tell. There's not many observations here to really make something. And when you go up to 5 bedrooms, quite frankly, things are going to be all over the map as far as their prices go. Finally, we also have Pre-tax operating margin, auto manufacturers. Kind of this random metadata, but again, we see normal distribution. Right, the ones in red, I believe. Oh no, the red is the average. For 2003 to 2012, and then the blue is the actual 2011. In both cases, you see that general shape. So that's my long way of saying this normal distribution, this bell-shaped distribution that we rely on, is not something that we pull out of nowhere. It really does have this kind of empirical grounding to it. It makes sense at some basic level that we use it. It's not complete bullshit. Now, granted, there are examples of a normal distribution which don't follow it perfectly. There are examples of, I should say, the examples of data which clearly are not normal distributions. If you think about people on a beach, so here's the beach, here's maybe the end of the pier, and then you measure the distance from the pier. Are you going to have a lot of people here and then a few people over here and a few people over here? No, what are you going to have? You might have more people at the pier. I was thinking like if they're set up on the beach, they might look kind of like this. Right? But if you're going to the beach, do you look for the place where lots of other people are? Like, oh, let's set up over there where it's crowded. Right. No, where do you look? Where it's less crowded, and that's going to result in what we call a uniform distribution, people being sort of evenly spread out. So that's clearly not a normal distribution. That's clearly not a normal distribution. So there are certain exceptions. I don't want to like claim everything is a normal distribution. A lot of things are. We can also fiddle with this a little bit too. Before we fiddle with it, let's also define a specific kind of normal distribution called a standard normal distribution. Or just called standard normal. Standard normal is defined as having a mean of 0 and a standard deviation of 1. A mean of 0 and a standard deviation of 1. You don't want to actually use what's it called? This. I usually use it. Yeah, I don't know. Now, we can take that standard normal and we can play around with it a little. As I was saying, we take the normal distribution, we'll play around with it a little bit. Because we recognize that in practice, the actual data can look a little bit different than our idealized version. So our idealized version becomes our standard, the one that we sort of reference to. We'll put that maybe in the center. And then we can note that it can deviate in a couple of different ways. One, you sometimes have data that looks like this. Or you sometimes have data that looks like that. These are clearly not symmetric. This is symmetric. I didn't really do it super well. Let's just pretend I did. Like that. And got the peak. And then bring it down. Oh, that was terrible. That was even worse. Don't pay attention to that. And that's also worse. And there we go. That's not bad. Not great, but not bad. But you see, like this one is symmetric. In other words, one half is a mirror image of the other half. Indeed, in this symmetry, the mean equals the median. But that's not going to be the case on the ones on the left or the ones on the right. What's the difference between the ones on the left and the ones on the right? So, you know what we call this depiction? Skew. So what's your name again? Robian is what does skew mean? Don't say when the data is skewed. Okay, I like that when the data is kind of pushed aside, right? Just like, not the whole thing, but just like a little bit of it, right? We would call this negative skew. Or sometimes it's skewed left. And what do you think we call this? Positive skew. Or when it is skewed right. Can anyone give me an example of data that's skewed left or skewed right? What an example of such data? In other words, data that maybe have lots of unusually really high observations, or lots of maybe unusually low observations.
Right. So maybe how many times people go to the gym every week?
Okay, so what's the variable? So.
How many people go to the gym?
Oh, I see. So you want to say it's positive or negative skew? Skewed Y. Yeah, so we can say like, I mean, quite frankly, it would look like a lot of people don't go at all. So it would be like that. But yeah, if we sort of focus on that, right, you get like a lot of concentration here, and then a few like gym rats. I think they're called gym rats, right? Is that the slang? Yeah. Begins with a D. I don't even have anyone. The only person whose name is with a D is David, so that's not right. I can predict. Anisha. So I'm in the first half of the alphabet. All right, Anisha. That's true, but a right-hander or left-hander, you're either one or the other, right? And we're sort of looking for something continuous, right? Anything else? Anything that might be skewed to left? Or at least somewhat continuous. How about GPA? So, does anyone know what grade inflation is? You never heard grade inflation? So grade inflation is a concern that comes up in academia a lot, that we allow grades to sort of be too high. Because as someone who gives out grades, I don't say give out grades, I say assign grades, I should say assign grades. No one ever complains about a high grade, but lots of people complain about low grades. So there's sort of this incentive to sort of bump people up a little bit. And then other people bump people up, and then because of the new standards, then you bump things up more. And then over time, the average grade kind of gets arguably too high. And that's what we see here. Like lots of people get A's, B's, and C's, and not many people get D's and F's. If we think about a scale of 4.0 scale, F is 0, D is 1, C is 2, B is 3, A is 4. So we're going 0, 1, 2, 3, 4. Or you can just in general say GPA. A lot of people have GPAs right here, in part because of grade inflation. There's also a sorting mechanism too. Like if you're going to get F's a lot, you're not going to be in school very long. There's a survivorship bias, but part of it is also grade inflation. Right? And that's going to cause you're going to see a left skew. Any questions on that? Yeah.
If you were to, can you use like a presidential poll, one of those ones?
Well, what are you polling? What are you asking?
Like maybe like two candidates versus each other, or like Republican versus Democrats kind of thing, or whether you like them or not?
It's tricky because if you like them or not, that's an on or off switch, right? That's like either you do or you don't. There's no like, now if you want to rate them as like, how do you feel about this person? And how do you feel about this person on a scale of like 1 to 100 or something like that? Well, now you can say, and now you can get something that looks more like a distribution because now there's no on-off, there's a lot of middle ground, right? Just like income is like this, right? It's not like you either make money or you don't make money, like that's what people care about. It's like, no, people care about the amount. They care about the scale. And now you can do a positive skew also of income. Few people make very, very little, and then we have some people will make more, and then as you get higher and higher, then that immediately drops off, and then there's like a few people that make crazy amounts. 6, 7, 8, 8. Any other questions? Okay. So, I want to keep this, but I want to make it a little shorter. I made it too big. Before I do that though, what is the relationship? Here we say mean equals median. What's the relationship between mean and median over here?
The grade is greater.
So I heard two different things. Is the mean greater than or less than the median?
Greater.
Greater than the median. Why? Why does that make sense?
The average looks like it's a little bit more towards the right side, close to the middle, the exact middle.
Mm-hmm. In other words, these unusually low values are kind of spoiling the mean. So I would say the opposite. I would say the median is higher. And we saw that when if you pull out my data from last unit and you see my distribution of grades, I think the median grade was a 3. It was a B, but the average grade was like a 2.9, something like that. I can't remember the exact number. Because these really low averages will drag the mean down. So the median actually ends up being larger. You can probably then guess what's the relationship between mean and median over here. The mean is bigger. And you see that with the data. When people report average income, it's always higher than when they report median income. We saw this with student loan debt. Average student loan debt is higher than median student loan debt because there's a few very large values that drag the median up rather than drag the median down, like we see over here. Any questions about this? So, see, I really need more. I don't know. The problem is I'm tall. I want to do things here. I really should be doing them here because that's screwed up. But I also want to change this in 2 other different ways. Right? Rather than looking at skew, I want to look at the sharpness or the peakness of the data. So I'm going to have to do this a little awkwardly. Versus okay. So here are 2 other distributions. Like the middle one, these ones are symmetric. Right? 1/2 equals the same half. So the median and the mean are the same. But there is a difference between them. What's the difference? How do they look?
Steepness. One is steeper than the other.
Yeah, exactly. This is what we call kurtosis. This is a measure of the peakness of the data. Peakness of the distribution. This one is flatter than normal. It's flatter than literally normal. So we call this a negative kurtosis. And this one is sharper than normal. It has a positive kurtosis. What do you think the relationship is between standard deviation and kurtosis?
One with a positive kurtosis is going to have a smaller standard deviation from
Patrick? Adam? No, you're Adam. Austin? Gabe? I was more down that list. Alright. Sorry about that. So the problem is like when you have an exam, and they're like, I literally don't like it, and then the weekend, I don't see it for a weekend, no idea. They say Rebecca or no. Gabe's absolutely right. So let's just say that again. So about the standard deviation, if we
for positive kurtosis, the data is close together, so the standard deviation is smaller.
Mm-hmm.
For negative kurtosis, opposite.
Exactly, because a lot of the variance, a lot of the variation is right around the mean in that case. So the standard deviation is going to be naturally lower. A lot of the observations are concentrated in the center. Well, with negative kurtosis, as Gabe points out, this indicates a higher standard deviation. Things are more spread out. You're taking observations, you're throwing them off to the side. And that's lowering the peak. There's fewer observations in the center and more off in the distance. Any questions? Yeah,
So you
Joyce?
said that-
Joyce, yes.
You said that it's a positive kurtosis because of what?
Because there's more observations concentrated toward the mean, toward the center. And as a result, the number of observations sort of inflates. The observations in the middle. Peak up. I always hate that, like the peakness. Every definition I've seen of kurtosis involves like the peakness of the data. And we have to put something in quotes. They're weird. All right, fine. All right. Any other questions? Okay. So these are just some of the ways that it can deviate from this idealized version. But whenever we get data, we don't necessarily have reason to believe that the population is one way or the other. Sometimes you do, you look at the sample data, oh, it's kind of skewed left, oh, it's kind of skewed right. But for simplicity purposes, and just because we really, you don't ever always know for sure. And so many things look like a standard normal distribution or a normal distribution, we always focus on the normal distribution. So let's unpack the normal distribution a little bit more. And get rid of all this stuff. And get rid of this stuff over here too. There we go. I wanted to really center this. I really didn't, so I'm just going to recenter it. Yeah, I didn't really do it. Oh, I think I got worse. Okay, just, it's okay. It's okay. All right, so let's imagine I have this mean here in the middle, and I go one standard deviation to the left and one standard deviation to the right. So I'll indicate that as a -1 standard deviation and a +1 standard deviation. Does anyone know what percent of the observations are captured within that first standard deviation? 68. How many of you knew that? No, you knew it. CJ, you knew it. Gabe, you knew it. You just knew it.
No, your notes.
Oh, okay. So, is that what you're looking at, Gabe, or do you just know it from another class?
Yeah, I already knew it.
You already knew that. Where did you learn that?
High school.
High school. So you know what the school is called that I'm establishing?
No, just play like CD.
Okay. But you knew it was 60. You remember the 68 number, but you don't remember what it was called. That's interesting.
That's a conversation for another day.
Let's go 2 standard deviations out. It should be negative. It's negative 1 sigma. So 1 standard deviation below the mean and 1 standard deviation above the mean. We actually do it this way. This is negative 2 sigma and a positive 2 sigma. Do it this way. I try to come up with new ways to sort of depict this. And that doesn't look symmetric because I think I screwed up. Yeah, that was a little screwy. That. What is, Gabe, do you remember 2 standard deviations? 95. We can box with this, we can box this one. And then we go 99.7. The 3 below. And 3 above. This is known as what's called the empirical rule. (68% of observations are within 1 standard deviation of the mean. (95% are within 2 standard deviations, and 99.7% are within 3 standard deviations. So note that over half are right there at the mean in 1 standard deviation. And you go out in another standard deviation. Of course, you're not only capturing that 68% still, but you're also capturing an additional 95 minus 68, which is 25%. Yes, 25% of observations, additional 25%. So, and then you go out an additional one, and now you're capturing maybe about 2.7% more. So you really see how much it drops off. That when you go 1% deviation, you get over half. But if you go out a third standard deviation each direction, you're only adding like 2.7% of the observations there. Right? It's a huge drop off, but it makes that bell curve. Any questions?
Honestly, man, I don't think we learned the rule.
We just know that 68%, 95%.
Yeah, we just learned like what it's. But yeah,
No, that's fine. Because what's great is that you get to go one step further even in this, because I'll teach you to not only, I'll show you how, I'll show you this rule, but I'll show you how to find the difference anywhere. So if you want to know, well, okay, what is at half a standard deviation in each direction? I'll show you that. What's the difference if you go one standard deviation below, but no more than half a standard deviation below? Over here. What about over this one? What about over there? I'll show you how to do that.
Is it always like 60? Like, does the error have to be like in the center like that, or is it still 60? It's like skewed?
Well, if it's skewed, then we're going to throw things off. Right. And if we play around with kurtosis, it's going to throw things off. So that's why I say, but let's start with the standard normal. Right. Even this is the normal distribution, right? Not doing anything wacky with it. Any other questions? So now that you're getting a little familiar with it, let's pull on one of the really fun things where it comes up. And this is sort of a hard thing to believe that this works. So I'm going to give you the rule, I'm going to give you the definition, and then I'm going to show you in Excel an example of how it comes up. It's a little weird. Oh, let me delete some stuff. Delete that, yeah. Delete that, yeah. Okay. Let's recall something that we talked about before, which is, I'll probably go, I know right over here. Samples. All samples have to be what? Begins with a P. No? Precise. She said it first. Precise. What do you mean by precise? What about that? Yeah. Jeanette. Okay. So, well, what did you say precise? I mean, you must have known why that precise is there. Anything? I know it's been like, a few days since you had the exam, so, I mean, naturally. Anyone want to help her out? We by precise? No, keep going, keep going. Accurate results. So keep in mind though, it's not about if we're biasing in one way or the other. It's more about accuracy. It's about precise. So we can have a really, if I had a sample size of 3, would that be a trustworthy sample? No, why not? No, what do you mean it's not enough? Why not? Well, how do you know? Oh, look at you, Magic Rolando. You know that 3 is not enough. Like, what's wrong with 3? Why? Of course the population is larger. That's why we took a sample. You're thinking of like you reduce sampling error, I think is what you're thinking of?
If you look for more data that you have to work with rather than just
So we have more information. But also, and I think what you're trying to get at, Rolando, and what everyone's trying to get at really, is like if you increase your observations, you make it less likely that you will get an unusual sample just by random chance. If I'm measuring the average height of Montgomery College students, and I don't want to literally measure everyone's height because I got things to do, so I take a sample, taking a sample of 3 means in all probability, there's a pretty good chance I got a few unusually short people or a few unusually tall people. And we could run some numbers. You can figure out, the likelihood of picking an unusually tall person, unusually short person, and then you can do a little probability, which we'll do in the end of the class. And you can see, that number's, it's kind of high. Right? That seems weird, right? But the likelihood that I pick 30 unusually short people or 30 unusually tall people, that's a lot less likely. Right? I'm much more likely, not guaranteed, but much more likely to get a good mix. Get a good representative sample, right? That this sample represents the population, and that is due not just because the sample is not biased, but also because the sample is just represented by those random fluctuations. The thing is, since this is all really about probability and the likelihood of choosing one versus the other, then we can mathematize this. We can say, how likely is it that I got an unusually small sample? How likely is it that I got something that was unusually big? And this is really an application of what we call the central limit theorem. It states that the sample means of a large size will be normally distributed regardless of the population distribution. Whatever large size means. So, regardless of what the population looks like, we can be pretty confident that the sample that we get will fall somewhere on a normal distribution, which means what the population actually is most likely to happen, but we recognize that things could be unusually small or unusually large. I've learned over the years that this is sort of a hard thing to really understand what's going on. So, and there's a couple of different ways to state this. That large size part is a little awkwardly thrown in there. I think I pulled that from some other definition that I found in the textbook. I don't really like that part. It's a little distracting because as you'll see, it's not really necessary. So, but sometimes people say it should be. A sufficiently large sample size is the population. It's weird. So, rather than sort of just telling you this definition and trying to get a really good intuition as to what exactly it means, what do you mean you make a distribution of sample averages? What are you doing? I'm going to show you with an example. And I've set this up in Excel in sort of this pure form to show you what's going on. And you can do this too if you ever have a free moment. It doesn't take very long to set up. I set it up before class today. So what I have is I have a table of numbers. And you can see I'm telling Excel to do a couple of different things. First of all, you see this RAND command. RAND is the random number command. It tells Excel, I want a number, you select it at random, it's somewhere between 0 and 1. So it could be 853, it could be 0.8396, it could be 0.001, be anything, right? Each number within this range is equally likely. In other words, it's a uniform distribution. Then I tell Excel, I don't want to work with super tiny numbers, that's dumb. I want a bigger number, so I'm going to multiply it by 10. So 0.68 becomes 6.8. Then I use the int command or integer command. Because I don't want to actually work with like 6.8, I just want to work with 6. So integer tells it to round it down to the nearest integer. That's what the integer command does. So as a result, I get a lot of different numbers. And I tell it to do it 5 times. So A, B, C, D, E, each one of those has a number in it. And then I ask Excel to find the average of these 5 numbers. So I've taken essentially one sample of 5. And I found one sample average. I then copied and pasted that 100 times, and I now have 100 sample averages, all taken from that same distribution, somewhere between 0 and 1, multiply by 10, take the integer. So again, this is a uniform population distribution. Every element has an equal chance of showing up. I pulled out 500 of these, set them up into 100 observations of 5 each. And I now have 100 sample averages. And I can tell Excel to then plot those sample averages on a histogram. And this is what I got. Does that look like a normal distribution to you, roughly? Yeah. Is it perfect? No. Like many of the other normal distributions we saw, it's not perfect. But it's pretty good. It's pretty good. And what's fun, too, is that if you hit the F9 button in Excel, you are telling it to recalculate. So it will pick a whole new random, pick 500 new random numbers. And when I do that, I get a new distribution. This one was kind of bad. That's unusual. But it still has that general shape of a lot more observations close to the center. And then it spills off to the sides. I hit it again. That one's good. Look at that. Look how beautiful that one is. That's pretty clearly a normal distribution. And I can do it again and again and again. I can just do this all day. And it will always give me something that is at least roughly a normal distribution. Sometimes it peaks a little too high. Sometimes it peaks a little too low. But on average, it's pretty good. In fact, if you press and hold it, it goes right. And it looks like you're really busy. So if you stare at it and then you concentrate, it looks like you're doing something really important. Now let's take a moment and develop the intuition as to why this worked out so well. Here's an example. I have very few observations that go from 1 to 2, the average of 1 to 2. Let's see if I can find one of those that were, oh, there's one. That was easy. Take a look at observation number 31. How did I get 1.8? There's one of mine right here in the 1 to 2 range. How did I get 1.8? The average, but what were the observations in that? Just read the numbers.
2, 3, 2, 0.
So I had 3 2s, I had a 3, I had a 0. In other words, I'm sort of picking stuff on the low end of the distribution here. Again, by random. Because when you're doing a bunch of stuff, each one has an independent chance, you're doing a bunch of random things, it is possible that you will occasionally, by random chance, get a bunch of very low numbers. That's what I did here. No different than, it's possible that if you spin a roulette wheel, you will get green like 8 times in a row. That's possible. It's unlikely, which is why it didn't happen very often, but it's possible. And that's what we're reminding ourselves whenever we pull a sample. We're reminding ourselves that it's probable this is pretty good, right? Most of the observations are right here. Most of the sample means are right here. But it's possible it's not. It's possible it's weird in some way. And by the way, if you were to do the same thing and you were to make all of these, rather than taking a sample size of 5, taking a sample size of 10, then the p-test would increase. It would concentrate more here in this section, and and fewer off to the edge. Because it's obviously more likely to get 1.8 when you're only working with 5 observations than it is to get 1.8 when you're working with 10 observations. That's why sample size is so very, very important in statistics. Any questions on this? My little CLT. That's a great one. All right, I'm distracted. So, let's switch over to Excel if you could fire it up for me. And by the way, I don't have a data set for you today. So instead, if you go to the desktop, right-click and then hit a new Excel document, new Excel sheet, or whatever it's called, you can go ahead and open an empty one. And we'll walk on it together as we explore some of the ways that we can see how Excel works. By the way, this says sheet 4 only because I was working through the last section. So I deleted that because I wanted to start it out. Excel has a couple of interesting functions when it comes to a normal distribution. 4, but it's really only 2. And so today we're going to be working largely with one of them. Hopefully, maybe we'll get to the second one. If not, we'll talk about it next slide. The 2 big ones are called normal or norm.dist for distribution, and norm.inv for invert. Normal distribution, the norm function, the one we're going to be starting with now, can do 2 different things. And you'll see this up, and I'll show you what actually happens. So, 1, if you put in an x value somewhere along the normal distribution, this distance, this probability, or this percent of total observation comes out. You can also put in x, and instead of just having the line come out on that particular value, you can have this value or less. This whole area comes out. You're going to want to put the arrow coming out. And this is what's printed. And I'll show you in Excel how to make the distinction between those 2, but you get both of those effects from the norm distribution command. So, let's have some fun. I mentioned before, what's it called? I mentioned before IQ. What is the average IQ? Does anyone know? Think I heard it? 100. Exactly. Maybe I'm curious, what percent of the population has exactly a 100 IQ? And I'm curious at maybe 4 different standard deviations. Now, I'll tell you right now, 15, at least 15 is the one I know. 15 is the one I hear about as to what the standard deviation of this is. So we're going to work right here, and then you'll see how this value changes when we change the standard deviation. So, what I want to do is I want to put in 100. I want to say who is exactly it, so that's going to be my x value. And then I'll define what the mean is of this distribution, what the standard deviation is of this distribution, and then I will indicate that I want exactly 100. So the first step is to type in norm this. You see it's that first option there. And the first thing that's asking you to do is x. X is the value we are curious about. Hey, what percent of observations are exactly X? What percent of people have exactly an average IQ? Well, 100 is the X. We want to know percent at 100 exactly. Our mean, so we put in a comma for our second argument for the second input. Our mean is also 100 because the average IQ is 100. If we want to know what percent of the population had a 90 IQ with the average of 100, we would put 90, 100. If we want to know what percent of the population has 150 IQ, we would put 150, 100. On state, comma. Any questions so far, by the way?
Can you explain the last part again about the 90?
So I'm doing 100, 100. It's because I want to know what percent of the population has exactly an average IQ, which means I have to put 100 here for what is the average of what is the mean, what is the average of the distribution you're working with. And I have to put 100 here because that's my x value, that's what I'm evaluating this equation at. So if I wanted to change it to what percent of the population has a 90 IQ, then I would change this first 100 to 90.
So the comma stands for deviation.
The comma stands for how you separate the arguments. So I don't, I'm done. I put in my x right here, so that's 100, comma, 100 for the mean, comma to separate it out. Now I'm going to put in standard deviation. And that I'm just going to reference A3. Because again, I want to see what happens when I change standard deviation. Then you can put comma again. And this is where things get interesting. It is asking for a cumulative function. So we know what that word means. Cumulative.
It's like everything from before.
Exactly. Like your final is cumulative because it's not just on the last material, it's also on the big ideas for the whole class. It's a weird word to say, so sometimes I say comprehensive instead because I have a hard time pronouncing things sometimes. But cumulative is what it's asking for. So it is asking if we want to use this cumulatively. If we say yes, or type true, or I always type 1 because it's faster, then we do this. We are asking what is the percent of the population who has an IQ of 100 or less. And keep in mind that cumulative function always means or less. But we don't want or less, we want exact. In which case we're going to use this, we're going to type in false or 0. I don't care which one you do, false is a little bit more intuitive, 0 is faster, I type 0. But I don't really care. Equal false. Over here, relative equals true, or 0 and 1. And then you're done. Then okay, hey, let's just for fun try to do a percent and throw in a strong value. So, what percent of the population has an exactly average IQ? 2.66%. Now, what happens, do you think, if I increase the standard deviation? So if I copy and paste this value and put it here, causing the standard deviation reference to update to 20. Oh, I just hit the percent button here, and then I threw on a couple of more decimal places. Because you need to, I add on some more decimal places. I am telling Excel Let me actually expand this too. I am telling Excel, I want exactly people. I want, what is the percent of the population, of the distribution that has exactly this value, in this case 100. If I put in the 1, which we will in a bit, you were telling Excel what has exactly that value or less. But I don't want or less, I just want exactly that number.
Question. Would you ever tell Excel to do 0 put like the sigma?
It's either 0 or 1, it's an on-off. For that last argument, you mean? Yeah. It's you see when you mouse over it, when you hit through it, it said true or false, right? You literally only have 2 things you can put in. So you can type in true or false. I always type in 0 or 1. That's what I'm used to doing. I don't care what you do. Any other questions? So what do you think happens if we bring it up to 20? Will it increase? Don't do it, just guess. Will it increase or decrease? Well, we have increase. So when we increase the standard deviation, we will see a larger percent of people who have an average IQ. Let's find out. Nope. It decreased. Why did it decrease? Why did it go from 2.66 to 1.99? Rolando? Exactly. If we're going to take the data and spread it out, that means we're going to be allocating at least some observations away from exactly the mean to off the mean. And so it has to, right? We're decreasing the kurtosis, so we're spreading them out more. Flattening out the distribution. Which means naturally, if we decrease the standard deviation, we're going to be bringing things closer. And thus we get a larger and larger percent at close to standard deviation. If the standard deviation was only 5, 8% of the population would have exactly average IQ. Exactly average. Any questions? Okay. Well, let's play around with that cumulative function again. This now I'm going to say percent 100 or less. Yeah.
How did you get the 7s and 8s at the B5s?
Oh, I just copy and pasted it down. So you should have made a reference to a 3. Yeah. Yeah. Oh, yeah. You have a. You want to change that? Thank you. Any other questions? Okay. So now I want to know what is the percent of the observations that are 100 or less. So rather than using this option, I'm going to switch over to this one, which all it requires me to do is change that 1 to a 0, or you could change your false to a true. Again, I like doing 1 and 0. It's faster, it's just one number. It knows what you're talking about, though. You can also just select it, I suppose, if you want. What do you get if you make it 100 exactly average or less? Yeah, 50%. Why is that? That was lucky. Huh. Why does that make sense? For what?
The data starts from.
Okay.
So 100 is the median.
Yeah.
This 100 or less is 50%.
Exactly right. It has to be. Right. It has to be. So obviously this is going to be half the data because we selected half the data. Right. 100 or less. And note that this is true, that this is still the case. If we copy and paste it down, we change the standard deviation. That hasn't changed the symmetry of the distribution. It's still symmetric. We're still divided in half. We just made it we just pulled it together more. We increased the peak distance. We made it steeper. Always going to be half. Let's do, to illustrate what happened, let me do this too, just so we're clear. So now I'm going to make a new column, but rather than putting in the average here for our first argument, we're going to put in 110. So we want to know what percent of the population has an IQ of 110 or less. Again, keeping an average of 100. Now we have a standard deviation of 20 because I'm referencing 20. And we're keeping it cumulative because we're doing or less. Switch that. Put another decimal place. That's one too. And what do you see?
Can you put a formula again? Can you put a formula again?
You mean the formulas? There we go. So now it's exactly the same, except now I'm doing 110 rather than 100. Any questions? Yeah. Any value or less. Yeah. And you can also, as we will talk about, you can use it to find any value or more, because the whole 100% of observations are underneath. So if you do or less, then you take 1 minus that to get or more. Yeah.
So in the equation, the first number is the one you're looking for, and this one is
Yep. And you see that when you type in, we type normal distribution, it says x, comma, mean, comma, standard deviation, comma, cumulative. So that's why I don't spend too much. I don't ask you to memorize it because Excel tells you. You can also, too, if you really want, when you're typing in the normal distribution, you can press that FX button. And if you press that XF button, it gives you the table of everything, including descriptors. So here's x, returns the normal distribution, specified x is the value for which you want the distribution. Then you hit mean. It's like mean is the average of your distribution. The arithmetic mean, arithmetic mean, the standard deviation, etc., etc. Yeah.
So for the first one, where it says 100 for the first one, can you use like the true statement because it was right at the center?
Because we're trying to find this value or less. So whenever you put in the cumulative function, you're not looking for just the value. You're looking for the value and less than that. So the percent of observation. So what percent of people have an IQ of, in this case, 110 or less? Not exactly 110. But including the 109s, the 108s, the 73s, the 64s, the 100s.
So if it said or more, which one would you choose, true or false?
Anyone know how we do this? So if this is or less, this is 100%, right? So if you want or more, you take 100% and subtract off this part. And what remains is there. Great question. Any other questions? So now you see if we increase our standard deviation, or if we decrease our standard deviation, then more and more are concentrated on that mean. Right now we're seeing the values change. All right, let's really get a good handle on this, and we're 10 minutes left. And let us take a moment and derive the empirical rule. Because if you were thinking, how the hell am I going to memorize the empirical rule? You don't have to memorize it. You just have to memorize how to figure it out itself. And not only will you learn the empirical rule, and figure it out, you can find out any number of other things too. It's a good way for us to get practice at working with this. So recall that the empirical rule goes 1 standard deviation up or down, 2 standard deviations up or down, 3 standard deviations up or down. That leaves us with 6 numbers we care about. -3, -2, -1, +1, +2, +3. So let's type in -3. Oops. The numlock is turned off. There we go. -3, -2, -1, +3. A +1, +2, +3. Make sure you do it that way. Where the -1 and the +1 are next to each other, and then it branches out. Let's center that too. There we go. Oh, let's put it in bold. Also. Yeah, we're not gonna get to normal invert today. That's sad. I like talking about it. We'll talk about it later. Now, what we want. Well, we're going to pull out something slightly different. So we're going to use our normal distribution as before. We're going to use not the normal distribution, the normal standard distribution, or normal.s.dist. What is a standard normal distribution defined as? Exactly, the mean of 0, a standard deviation of 1. So note that when you put in norm.s.dist, it's not asking for mean and standard deviation. That's built into the command you put in. So by using norm.s.dist, we're just saving a couple steps. You can, if you want, just use norm.dist and then put in mean 0, standard deviation 1. But this is faster. It also is asking you for z, which for our purposes is the same thing as x. And I'm just going to highlight A1. Because this would reflect 3 standard deviations below the mean. If we establish a standard deviation of 1, this is 3, and negative means it's to the left. We also want the cumulative function, because we want the value or less. Hit enter. Copy and paste across.
You're getting so little to put out the books behind.
Can you shut the door, please? We only have a few minutes left, so let's make the most of it. Okay. So when you do that and you copy and paste it across, does anyone need me to pull up the formulas? Is everyone good? Everyone on the same page? Yeah? Yeah? So when we do this, we have a bunch of these values right here over and over again. Go to the left, then we go a little bit closer to center, then we go a little closer to center, then we go off to the right, farther and farther. And so you see that they increase, going from very small numbers to larger and larger ones, all the way up to 99 point whatever it was, 0.99 whatever. But we don't want that. We want this. We want 1 standard deviation from the mean in either direction. How do we find that? Let me give you a hint. This C2 I should say, C2 reflects this area right here. And D2 reflects, remember, that value or less. That area right there. But we only want this part. We'll give you a moment. Highlight these 2 areas from C4 to D4. Let's merge in center. Let's make a little border for them too. That'll be fun. And what'd you say, Ike?
D2 minus C2.
D2 minus C2. And 68%.
How do you get rid of the middle?
Merge, I hit the merge and center buttons. So I highlighted both of them, and then I pressed merge and center. So it'll merge the cells, and then center the cursor. I can then do these 4, going from B5 to E5. Press that merge and center button again. And I like to make borders, so I'm just going to make a little border here under the font option. Ooh, and you know what? As long as we're doing it so it comes out nice, so let's hit that percent. And we go E2, which is that large area all the way down, but we don't need anything past. We're going to subtract off the extra stuff that's way at the end of this tail that we don't want, because this is past 2 standard deviations. Hit the button again, 95%. Just like the empirical rule says. Remember, 68, 95. And what was the last one again? 99.7. Well, let's see if we got that. Equals this, and of course we have to switch it, give it another decimal, 99.7. Of course. So you can see the individual formulas and you can sort of guess what the rest of it should be. But this is us just deriving the empirical rule. And because we established these values, if you want to know what it is, half the standard deviation between each one, you can put in negative 0.5 here and a positive 0.5 there, and you'll get a new value. If you want to know what is it between 1 standard deviation below, but we're going to just now do nothing above the mean, then you can put 0 here and keep that -1. Or you can do that as a negative 1.28 if you want. You can get any number of things. You can see exactly where everything lies. And this makes more sense. It's more intuitive. It's kind of more enjoyable if you attach value to it. You might know your IQ. Maybe your IQ is like 120. What percent of the population am I smarter than? Well, put in 120 with a 100 average, 15 standard deviation, cumulative function, and that's the percent of the population you're smarter than. And they'll send us out the issue now. IQ, yes, is an imperfect measure of intelligence, yada, yada, yada. Not a psychology class. Any questions? No? Okay. And I'm out of time. So I will see you on Thursday, where we'll pick up and we'll go into normal invert. We'll do the opposite of what we were doing.